Hello, welcome to the second unit, Matrix Eigenvalue Problem and Quadratic Forms. In this lecture, we are going to see how to determine the eigenvalues and eigenvectors of a matrix. Let us consider first the transformation. So if you consider this transformation, 5x plus 4y equals to u, x plus 2y equals to v. So this is a transformation. 5x plus 4y equals to u and x plus 2y equals to v. So if you write this in the matrix notation, you will get this one. So 5, 4, 1, 2 and xy uv. So here this 5, 4, 1, 2 is the coefficient matrix, and xy, it is a column vector of unknowns, and this side uv, it is also a column vector of constants. Okay. Now what this transformation tells is, this transformation transforms this vector x comma y to the vector u comma v with the help of this coefficient matrix. So this transformation transforms the vector x comma y to the vector u comma v with the help of the coefficient matrix here, which is 5, 4, 1, 2. For example, if I take xy equals to 2 comma minus 1, xy is 2 comma minus 1, then if I operate with this matrix 5, 4, 1, 2 over this 2 comma minus 1, it transforms to 6 comma 0. It transforms to 6 comma 0. If you see geometrically, right, if you notice the vector 6, 0, whatever the resultant we got here 6, 0, which is not along 2 comma minus 1, that you can see it here clearly. So the vector we have taken is initially this one. In this figure 1, if you see, we have taken xy as 2 comma minus 1, and if I substitute this in this transformation, the resultant vector we got is 6 comma 0. Clearly you can see this vector 6 comma 0 is not along the direction of 2 comma minus 1. Okay. Now in general, the vector u comma v, this one, will not be along the vector x comma y. In general, it is not possible. The resultant vector u comma v is not along the vector x comma y. But there are some special cases are there where the resultant vector is in the direction of the vector x comma y. So that is here. However, it is possible that there exist some vectors x comma y such that the transformed vector, this one, and the original vector, this one, will have the same direction. For example, if I am taking xy equals to 4 comma 1, if I plug in that xy equals to 4 comma 1 here, and if I operate with this matrix, so the resultant vector we are going to get is 24 comma 6. And if you see, the direction of this vector is along the direction of the vector 4 comma 1, that you can see it clearly in the picture here. So the original vector we have taken is 4 comma 1, and this vector is transformed to 24 comma 6, which is clearly in the direction of the original vector. Okay, so this type of cases are very rare. So hence we observe that while the transformation, this one, in general changes the magnitude and direction of many vectors x comma y after the transformation, there exist some vectors x comma y whose direction will be same as that of the transformed vector u comma v. So such type of vectors are known as the eigenvectors. They are also called the characteristic vectors. So they are known as the eigenvectors or characteristic vectors. So eigen is the German word. The meaning is characteristic. So which is known as the characteristic vectors. Now we are interested to find the characteristic vectors or eigenvectors. Now we'll see, let us see the fundamental definition. Suppose A is an n by n matrix. A non-zero vector x is said to be an eigenvector of A if there exists a scalar lambda such that Ax equals to lambda x. Whenever this condition is true for a non-zero vector x, then we say that this x is known as the eigenvector and this lambda is known as the eigenvalue. So if Ax equals to lambda x, if whenever it is satisfied, where x is a non-zero vector, remember always the eigenvector is a non-zero vector, then we say that this x is an eigenvector of A corresponding to the eigenvalue or characteristic value lambda of A. So this is also known as the eigenvalue or characteristic value. How we are calling this one as eigenvector or characteristic vector. So this is the fundamental definition of eigenvector. Now we'll see the procedure how to find the eigenvectors of a matrix. So let A is any n by n matrix. So we are assuming that x is the eigenvector for this matrix A. Then by definition I can write it as Ax equals to lambda x. So lambda x. So if I am multiplying this x with unit vector, so once again we will get the x only. So what I am doing is I am bringing this lambda x to this side and we are writing like this: Ax minus lambda ix equals to 0. It is not 0, it's a 0 vector. So if you pull out this x outside, you will see a minus lambda I into x equals to 0 vector. So if you look at clearly, what is this? This is looking like a homogeneous system of n equations because our matrix A is n by n in n unknowns. It is a homogeneous system. So this will have a non-trivial solution whenever the det of this a minus lambda equals to 0. So in order to be a non-trivial solution, right? So the determinant of this must be equals to 0, right? Because one more logic is here. This is product of two terms, and if you see this one and this one, x is clearly a non-zero vector, so definitely this must be equals to 0, right? So, and one more thing is here, this will have a non-trivial solution x if and only if the det of this must be equals to 0, because it is looking like a homogeneous system of n equations in n unknowns. Now if I equate this equals to 0, what I am going to get is a characteristic equation, which is a polynomial equation in lambda, which is a polynomial equation in lambda of degree n. So because it is a polynomial equation of degree n, what I will get is, I will get roots. How many roots I will get? N roots by solving that one. So let us assume that these roots as lambda 1, lambda 2 and so on, lambda n. So these are the eigenvalues of the matrix. Now corresponding to each and every eigenvalue, we have to calculate the corresponding eigenvector. So to calculate the eigenvector, what we will do is we will plug in these lambda values one by one into the system. What is that system? Is this one: a minus lambda I into xi equals to 0 for I equals to 1, 2, 3 n. That means I will bring first lambda 1 value, I will substitute here so that I will get the corresponding eigenvector. For lambda 1, I will get the corresponding eigenvector. Similarly, I will substitute lambda 2, I will get the next eigenvector. So this is the procedure to solve the eigenvectors of a matrix. It's very simple. First thing is, for the given matrix, you have to calculate the characteristic equation. Solve that characteristic equation, you will get the roots. So substitute each and every root in the system and you will get the corresponding eigenvector. Now we'll see one problem, how to calculate eigenvalues and eigenvectors. So this is a matrix of 2 by 2 order. So first what we have to do, we have to calculate the characteristic equation. Characteristic equation means det a minus lambda equals to 0. So this is a minus lambda equals to 0. So 8 minus lambda minus 4, 2 minus lambda equals to 0. So it is a minus lambda I. What is I? I is 1001 unit matrix. So from this I am subtracting minus lambda into 1001 means lambda 0, 0 lambda. If I subtract, I will get this one. So now I have to expand this one. 8 minus lambda into 2 minus lambda plus 8 equals to 0. If I multiply this, I will get lambda square minus 10 lambda plus 24 equals to 0. So it is a quadratic equation. If I solve this, I will get the roots is 4 comma 6. So these 4 and 6 is acting as the eigenvalues of the matrix. Now I have to get the corresponding eigenvectors. So to get the corresponding eigenvectors, consider the system. So this is the system. 8 minus lambda into minus 4, 2 into 2 minus lambda into xy equals to 0. This is the system I have to consider. So in this first I will substitute lambda equals to 4. If I substitute lambda equals to 4, 8 minus 4 is 4, minus 4, 2 as it is, 2 minus 4 is minus 2, and remaining is same. Now what I will do is I will make this one as the upper triangular matrix. To make it this one as the upper triangular matrix, what we are doing is here, right? So I am multiplying row 1 with minus 1 by 2, and then I am subtracting row 2 minus 1 by 2 times of row 1. Therefore, I will get this is 0, 0. So from this I will get 4x minus 4y is 0. So which is x minus y is 0, x equals to y. So what I am doing is I am choosing y equals to k. If I choose y equals to the k, then I will get x equals to k. So xy, so k, k, k. If I pull out this k outside, 1, 1. So where k is not equals to 0, which is a scalar. So if I choose k is 1, I am going to get the first eigenvector corresponding to the eigenvalue lambda equals to 4. So same procedure we have to do it for lambda equals to 6. So substitute lambda equals to 6 in the system. Then you will get this equation 2 minus 4, 2 minus 4, xy equals to 0. Once again make this as upper triangular matrix. So for this I am doing this row operation. What I am doing is R2 minus R2. R2 is here 2 minus here R1. R2 minus R1 it is. It is not 2, R2 minus R1. So if I do R2 minus R1, I will get 2x minus 4y equals to 0. From this x equals to 2y. So here I am choosing y equals to k. If I choose y equals to k, I will get x equals to 2k. Therefore, my eigenvector is xy. What is x? 2k. What is y? K. So I am taking out this k outside. So 2, 1. So where k is not equals to 0. So 100% it must be not equals to 0. Otherwise, you will get a 0 eigenvector, which is not possible. So if I choose k equals to 1, so 2, 1. So this is the eigenvector corresponding to the eigenvalue lambda equals to 6. So this is a simple procedure to calculate the eigenvalues and eigenvectors of the given matrix. I hope you understood this. So I am Srikanth Reddy. Thanks for watching this video. I will see you in the next video.